Hello, this is Rex, and this is the final version of my counting circuit. So as you can see, it has a switch which can turn on and off. There's a button which can make it either count up or count down. So the NAND gate oscillator is essentially the first part of the counting circuit. So the resistor is in the pull-up configuration, and that allows for low side switching with the button. So at rest, pin 12 and 13 are both high, which would output a low at pin 11, and after the low signal goes through D1, pin 1 will receive a signal of low, and since we don't know what the input of pin 2 is, we can assume that pin 3 has an output of high, since according to the NAND truth table, as long as there's at least one input of low, the output is always going to be high, and pin 3 then goes through R4 and R3 to input a high signal into pin 2. And then pin 3 leads on to both pin 5 and pin 6 and inputs a signal of high, which would output a signal of low at pin 4, and then pin 4 would input 2 low signals at both pins 11 and 12, which would output a signal of high, which would not allow the LED to turn on as it has no path to ground. The difference in charge between pins 3 and 4 also charges the capacitor in C2. So when the button is pressed, 12 and 13 would both become low, making pin 11 high. As a result, the capacitor charges instantly in C1, and some current trickles down into R2. This signal then converts onto pin 1, and since there are 2 high signals, the output at pin 3 becomes low. This then makes the LED turn on as pin 4 becomes high and pin 10 becomes low, which gives LED a direct path to ground. Since pin 3 is low, C2 discharges through R4. Once C2's charge reaches below half of that of the supplied voltage, pin 2 becomes low. This makes it so that pin 3 outputs a signal of high, which makes the LED turn off. Since pin 3 is high, C2 begins to charge again, and once its charge is above half of the supplied voltage, it goes through R3 and makes the input on pin 2 high again, which makes pin 3 output a low, which turns on the LED again. This is essentially how the circuit oscillates. RC1 controls the duration of the square wave, whereas RC2 controls the frequency of the square wave. The square wave generated by the NAND gate oscillator circuit is then passed on to pin 14 of the 4017. The only purpose of the 4017 of the circuit is to divide the frequency of the square wave by 10, because otherwise the frequency of the square wave would be too fast for us to perceive. Moreover, pin 15 and 13, the reset and the stable pin of the 4017, to be conditioned, which in this case means that they have to be grounded. The divide by 10 output is inputted into the pin 15 of the 4510. The 4510 counts each of the rising edges of the clock signal and turns it into a binary number on its output. It counts from 0 to 9, and then it resets back to 0. The preset carry in, up, down, and reset pins needs to be conditioned for this chip to work. The up-down pin determines whether the circuit will be counting up or down. For this circuit, I connected a potentiometer to the RC2 part of the NAND gate oscillation. And what it does is when you start counting, when you turn it, when you decrease the resistance, it starts to count faster. And when you increase the resistance, it starts to count slower. There is also a up-down switch connected to both of the up-down pins for both 4510s, which can make it either count down or count up. Finally, there is also a reset switch, which can make the entire circuit reset. In order to achieve the two displays, I had to link two 4510s, utilizing the carryout pin from this first 4510 and linking it into the clock signal of the second 4510. Then I connected the second 4511 as usual, and also connected the dot to power. The 4511 decodes the binary signal from the 4510 and presents it into the format of a 7-segment display. In order to achieve this, it uses many different arrangements of different logic ICs. The 7-segment displays counts the clock signal in decimal form. I use resistors to drive the two displays as there is no built-in resistance within them. Thank you so much for watching, and I hope you enjoyed listening.